Yeah. Right. Right. So, hello everyone. My name is Stefan, as Carlo introduced me. So today I'll be talking to you about my PhD thesis, where I explored how to design and model deceptive machines. And I'll be covering the idea of computational deception, or using computational methods to represent and model deception in multi-agent systems. And then at the end of this presentation, we'll probably discuss about a multi-agent systems framework to enhance deception analysis. So at the beginning of my thesis, I go through multiple aspects of deceptions, like philosophical aspects, psychological, and some elements from intelligence analysis. So these three aspects complete each other. So if we want to understand deception, we need to understand the multitude of ways in which it can be defined. And that's covered by the philosophical theory. And then you have components that play in the real world, which have been explored in psychology and the cognitive sciences, like what actually happens when deception happens or doesn't happen. And then there are aspects from intelligence analysis that mainly try to understand deception in the real world, and they propose different ways of understanding it in the real world. So they're like, for instance, how it can be explained, prevented, caused, so on and so forth. So starting with philosophical definitions, there are two main approaches to defining deception. The first one is the deceptionist definition that includes deceptionist definition of lying, and then the non-deceptionist definition of lying. But again, these are ways in which people have referred to deception through the lens of lying, but deception does not necessarily mean one has to lie. You can easily deceive by telling the truth, but that means exploiting other people's biases and understanding of the world. So mainly the deceptionist definition of lying is the fact that you have an intent, right? That you want, so you're intending to cause a false belief, whereas the non-deceptionist of lying is when this intent is meaning. So you're just lying. When you're lying, you're merely stating something about the world that isn't true without intending anything about the other person. And then there's the third category, bullshit, which is now extremely prevalent due to the GPT-3 technologies. And well, I'll talk about that later, and I'll explain why a GPT-3 engine merely states bullshit. But yeah, whatever. So in terms of actual definitions of the deception phenomenon itself, apart from the distinctions between deception, lying, and bullshit, there are several ways in which we can define deception. First one is a non-functional definition. Non-functional means that we define something by enumerating all the ways in which it can happen, like lying, paltering, bullshitting. All of these things are ways in which deception can happen. But this merely, non-functionalist definitions do not actually explain the phenomenon itself, whereas functional definitions actually try to refer to what happens during deception. It defines it as a process. And of course, this distinction, you can find it in the paper by Artiga and Paternotte, but also in my thesis. All right, so after the philosophical definitions or distinctions, we have several theories in psychology and communication theory, so mainly social psychology, that try to understand deception. So first, there's information manipulation theory 2. Yeah, I know it sounds weird because it's 2. It's the second one. The thing is, when information manipulation theory 1 came out, it wasn't really a theory about deception. There were more some ideas of Stephen McCornack's in a paper. But then they tried to kind of like hypothesize about cognitive processes that were leading to deception inside the minds of people. So when they were interacting, so then they came up with information manipulation theory 2. So information manipulation theory 2 is a testable theory, whereas information manipulation 1, it was more kind of like a cluster of ideas. Then there's interpersonal deception theory. Okay, so information manipulation theory talks about the underlying cognitive processes responsible for deceptive speech production, but also for interpreting information that during communication. So it's all about how people plan, think, process information during communication. So what are those underlying cognitive processes? Then there's interpersonal deception theory that's not about the underlying processes inside the minds of the agents, inside the minds of the people, but it's more about the social cognitive factors like leakage, trust between agents, truth bias. So all of these things are in the interpersonal deception theory, including cognitive load, which means the difficulty or the difficulty of someone trying to deceive is regulated by cognitive load. They also talk about communicative skill and the relation between communicative skill and cognitive load. So the more communicative skill you have, the less is going to be your cognitive load when trying to deceive or detect deception. But there's so many other factors involved in interpersonal deception theory. The good thing about the theory is that it assumes an interpersonal context. So deception just doesn't only happen in the mind of a single agent, but it's out there, it's social, it's happens between agents. And then there's truth default theory that doesn't necessarily focus on the internal cognitive processes or the social factors that constrain this type of information passing, but talks about the context in which deception happens. And one of the important findings of truth default theory is that humans usually start their social interactions having a truth bias. So apparently, when we interact with people, we automatically assume that they're telling the truth. And we're triggered out of this truth bias when something that surrounds us, so when the context shifts. So there's some obvious information in our social context that makes us think, hold on, wait a minute, something's fishy. And then you become skeptical and start to interrogate what's actually going on. But otherwise, if you actually don't perceive any unusual information in the context, you just assume you stay in the truth default state. Right. Now, taking the philosophical definitions and the psychological or cognitive processes, we go on to intelligence analysis. So intelligence analysis wants to actually understand what's going on, taking into account, social phenomena, events. Well, it's mostly the mix between cognitive processes and events, but also philosophical theories of categorizing various types of deception helps, because you're actually trying to understand, and the way you understand it, you need to categorize it and create concepts. And the main contributions from intelligence analysis is Richard Hoyer's structured analytic techniques that mainly tried to devise methodologies for people who wanted to understand whether deception was happening or not happening, using a very rigorous methodology. And these types of methodologies were designed such that cognitive bias was reduced. The problem with such techniques is that they put lots of cognitive load on the analysts themselves, because you need to be very rigorous with when you're analyzing incoming information. For instance, who is the source that I got this information from? Does this incoming information falsify any other previous information that I had about the topic at hand, and whether I have any other information that makes me think that this source that I got the new information from is trustworthy or not. And then you need to think about the motives of your sources and so on and so forth. So you're mainly trying to explain is like an overarching narrative, at the end of which you will have a report that says, oh, deception is happening or not happening, maybe given some likelihood if the analyst is comfortable with probabilities. Right. So the main thing in intelligence analysis is understanding how deception is caused and how it is prevented from being caused, whether it happened or it's happening, and mainly also acting on it. Another issue in intelligence analysis is planning for deception. So when we think about deception and deception causation and prevention, it's also good to understand these phenomena in order to think through, possible deceptions that you might do. So yeah, right. So what I propose in my thesis is actually to understand deception using a multi-agent systems approach. And the reasons I propose this approach is because you're able to model not just arguments or signal processing, but you're able to model multiple cognitive agents, the relations between them, the environment in which they act, and what their actions in that environment, how they act on the environment, how they cause changes in that environment, but not only on the environment, how they cause changes in the minds of other agents, or how they manipulate that knowledge. And that's crucial to understand whether deception is caused or not. And this idea isn't really new, so to use the multi-agent systems approach, but it hasn't really been done. It was initially proposed by Cristiano Castelfranchi as a way in which humans would better understand deception and trust in virtual societies. In societies in which you wouldn't have only humans interacting with each other, but you would also have machines. So Castelfranchi's idea or argument was that the relations between humans and machines will change once these machines would get, when their autonomy would increase and their cognitive capabilities would increase. And in order to understand such machines, we should model them. So understanding these agents through modeling them. And then once you've modeled them, you plug them into multi-agent systems to actually understand interactions between different artificial agents, but also between artificial agents and human agents as part of large, complex hybrid societies where humans and machines interact. Right. So taking all this background kind of like paradigm into account, in my thesis, I asked two main questions. The first one is, can we use AI agents to improve our understanding of deception? But soon after I asked that question, I came to realize, in order to answer this question, we must first understand how may artificial agents deceive. So if we don't know how they're going to do it, then we can't actually, use them to understand the process. So if you want to understand, the overall process, you need to understand multiple components. And artificial agents are a crucial component because they're actually used to not only model artificial agents, but try to model the cognitive processes that humans that are triggered in humans when they're involved in deception. So then I immediately decided, okay, if we want to understand deception as a process, the best thing to do is to define it functionally. And this is the definition we came up with. So the intentional process of an agent, the deceiver to make another agent, the target, to believe something is true or false, that the deceiver believes is false or true, depending on the context, with the aim of achieving an ulterior goal or desire. So deceivers don't just do deception for deception's sake. Usually there's something else going on. They're doing it for a certain motive. There's a rationale behind it, especially in sensitive contexts, such as intelligence analysis. So you want to kind of like understand why someone is doing something and whether that is actually deception or is just, truthful or honest behavior. Right. Lots of people ask me, well, is it ethical that you're, designing or creating machines capable of deception? And my answer, well, yes, but it depends. And you need to argue. Like I hold the perspective that if you're playing with deception or artificial agents, you as a researcher, scientist, you should be able to argue why you're doing it. And there's actually a very nice method to do this called reflective equilibrium, in which you're trying to analyze all of the reasons why you're doing something and whether the thing that you're doing will actually have beneficial consequences. So first, there's the principle of non-maleficence. So modeling deceptive agents is not done with the intention to harm anyone, right? So the principle here is respected because you're not designing them to throw them out into the world and deceive people. But that is automatically related to the beneficence principle. Well, why are you doing it? Well, I'm doing it because I want to understand deception better in the real world between humans, but also how to understand the deceptive phenomenon between humans and AI agents. And in order to do this, we need to model them. Then there's the intellectual freedom principle that mainly says, well, if it's an exciting topic, then you should be able to explore it. I believe that deceptive AI and deception is an exciting topic. So that's, of course, very subjective, but yeah, it respects that principle. Then there's the openness principle. And the openness principle merely states that, right, you're doing some sort of research. This research needs to be open, especially to critique. And yeah, sure, I want to share this research with everyone. So if there are any comments, I can address them. And then the honesty principle. So is what you're doing actually promoting honesty? And some people would say, well, you're creating deceptive machines, therefore you're doing the complete opposite. Well, actually, no, I'm creating deceptive machines to understand deception and try to mitigate its effects, detect it, and consequentially promote honesty. So there's like this kind of like, well, not a long argument, but there's like this interrelated argument between the principles that I presented in my thesis. And all of this work, so needs to be a coherent, so we need to have a coherent justification of why we're modeling deceptive machines. And I think the distinction between my work and work in AI that, well, uses techniques that are not transparent or interpretable is quite major, because I'm doing this to understand it. And I want to look at the internal mechanics, but also on the emergent properties from these mechanics. If you're just, doing deception with a black box, you just cause behavior. You don't actually understand how it's happening and why. Right. So now going to the actual conceptual framework of my work. So there's some things we need to assume about deception if we wanted to actually understand how it's caused or prevented from being caused in the multi-agent system. The first one is you need to assume that deception is intentional. If you don't assume some sort of intentionality, then it means deception is produced at random, or deceptive behavior is simply generated due to some correlation in the overall system. If deception isn't intended, then it means there's no actually deliberative, there's no existing rationality or cognitive process in the agents that are actually attempting or trying to attempting deception, right? Or behaving in a deceptive way. The other one is we need to assume social abilities. Deception is social. It happens between agents, right? When some behavior that is deceptive is produced or being caused, or something is communicated, that affects other agents in the system. You can't have a single agent in an environment trying to deceive. It's simply like pointless. Of course, there's the case of self-deception, but that's kind of like another dyad that goes into these layers of representation of the self. So there's like, you could argue that there are more than two agents represented in self-deception as well. And there's also the, yeah, they're like, it's a bit tricky. Yeah. Then we need to assume that it's a multi-agent system. That's, of course, related to the assumption of social abilities. Another assumption that we make is that, at least for AI, you need artificial theory of mind. So when agents deceive, they need to think about whether they cause false beliefs in other agents that they think, that they believe to be true. And in order to do this and plan for this and deliberate about this, they need a model of the other agents' minds. So before they act, before they communicate something, they're like, oh, is this person actually going to believe something? Is this person or agent going to have a false belief if I decide to communicate this? Or should I actually communicate in a different way, say different things, or actually prepare that agent with some background knowledge in order to cause it to have a false belief? Or is there any inference mechanism, or is there any, does the agent that I'm targeting, is it using some sort of protocol for thinking about the things that I'm saying that I can actually exploit in order to cause the false belief? So you need to have a model of the other agent's mind. The other assumption we need to make is the causality of communication, right? So all of this, intentionality, social abilities, multi-agent system, artificial theory of mind, are rendered useless if we don't assume that what the deceiver is saying or communicating or acting doesn't actually cause any changes in the minds of others. And then we also need to assume contextual knowledge. All of this happens, speech production, communication, delivering of arguments happens in different contexts. And the context can change the deliberative process of the deceptive agents, but also of the targets. Right, so assuming that conceptual framework, I categorize the types of computational deception in different ways. First, we have one-way deception. In a one-way deception, we represent the process that goes one way. So from the deceiver to the target. It's, well, this is kind of like the foundational process that happens everywhere when we talk about multi-agent system deception. And when we model one-way deception, we only model a one-way process. Then there is counter deception, in which, well, both the deceiver and the target deceive and are being deceived, or trying to, like, you model it the other way around, and there's some sort of recursive representation as well. Then there is self-deception. I talked about this before. I actually haven't modeled that, but I can point you to like relevant references, especially from the perspective of dynamic epistemic logic or epistemic logic. And then there's distributed deception, which is mainly just a large, like, I think of it as a large scale model of social interactions where deception might happen. And you have, in distributed deception, in large scale systems, you have multiple types of deceptions where you have multiple deceivers trying to deceive a single agent, right? So think of collusion, for instance, or conspiracies, right? So there are multiple agents trying to cause another agent to have a false representation of the world. My best example is the Truman Show movie, right? So that's a perfect example of a type 1 deception. Then you have a single deceiver and multiple targets. This can be, you know, just a politician communicating to the public something, right? And then multiple deceivers and multiple targets, which is actually the most interesting one, because it's the, well, multiple deceptions and deception detections processes are happening in parallel at the same time in a large and complex system. So this is like the final stage, right? And we can explore these with different methodologies, right? And the approaches in multi-agent systems that I used were, well, deal with deception at 2 levels of abstraction. The first level of abstraction is the cognitive level. So here we're actually looking inside what happens in the minds of the agents, how their beliefs are being updated, how communication between agents causes these beliefs to be updated, how they produce persuasive arguments, not necessarily persuasive, more like deceptive arguments, what types of reasoning are involved in producing deceptive communication. And so modeling from this way, in this way, you actually look at an interactional layer. So you're looking at the actual interaction between deceiver, target, or deceiver versus target, depending on the level of recursivity. And then the other method is, or level of abstraction, is the social behavioral one. So basically in here, we assume all of these capabilities. So we assume that this is happening inside the minds of the agents and, you know, in like agent to agent interaction. And then we ask, okay, what if these things happened all at once in parallel between 2 agents, 5 agents, n agents, right? So this is like a system of agents, a population, or a network, or whatever you want to call it. And important, so here, the important elements are agent architectures and dynamics of like dynamic agent architectures. In here, the important concept is emergence. So assuming these rules, what kind of behavior emerges and how can we study it? Right. So let's go into the cognitive level. So in the cognitive level, what I've done is design some formal representations and rules such that we represent practical reasoning. And I use standard belief, desire, intention architectures because they're, well, they're the most kind of like mainstream and well-known practical reasoning representations in multi-agent systems. But also I've used them together with like elements of speech act theory. Speech act theory is actually very important because it assumes all the kind of like locutionary and illocutionary forces that drive communication. And one important aspect of speech act theory is that what you're communicating triggers chains of reactions in the environment and in the minds of other agents. So that was quite crucial. Then, of course, there's the part of theory of mind. So this was actually one of the trickiest bits of the approach. So how do we actually represent, how do we actually use practical reasoning and speech act theory to simulate what goes on in the perception of the targets? And that's how deceivers kind of like, they deliberate, right, about communication, about belief changes in the minds of others. And then, you know, we have communicative interactions, but also, again, important, this is not simply, so what's mostly been done with BDI and speech act theory, they didn't assume actually uncertainty. Whereas in deception, actually there is some uncertainty that are influenced by factors of deception. And these have been taken from interpersonal deception theory, information manipulation theory. So in information manipulation theory, there are two main cognitive processes, parse pro toto and totum ex parte. So parse pro toto is parse for the whole. So this process means that the deceptive agent is reasoning about what bits of information do I need to provide another agent in order for that agent to reconstruct the world in the way I want that agent to reconstruct the world, so for the purpose of having a false belief or some other ulterior goal. Totum ex parte is a sub-process. Well, it's not actually a sub-process, depending on the level of interpretation. But totum ex parte is the process in which incoming information is being extracted by a target agent or the receiver, and how it reconstructs the world using that partial information. So when agents are actually deceiving, they're engaging in both of these processes. And theory of mind is absolutely crucial for this, right? So in order to model theory of mind in multi-agent systems communication, we used operational semantics. So using operational semantics in a novel way meant that, okay, so previous work in theory of mind in multi-agent systems was using, for example, Bayesian optimization, planning, whatever. The problem with that is that in planning or Bayesian optimization, you already have the domain that is being specified. You already have a network of beliefs that you then reason over, find the shortest path, whatever, maybe given some uncertainty. With operational semantics, it's a bit different because we also explain the types of inferences the agents can perform in order to create new nodes in the domain with some level of uncertainty. So you can think about it as a consequence engine. So it's not something that you necessarily use backward induction immediately, but you're generating the world, you're hypothesizing about the world, you're using the mental model of the other agent to infer how that agent would create its internal representation of the world. And once you go, through a few iterative steps on that, you have this domain, right, that represents the mind of the other agent that you created through understanding how that agent performs inferences, and you simulate how it creates this representation of the world. And only then you use backward induction actually to find the best information that you can actually deliver it in order to make the agent actually infer one of the paths in the multiple paths you actually simulated that agent can actually create in its mind. Right. And of course, there's so many other things involved. And this is mainly an abductive process that the deceiver goes through. And it's not simply a recursive process like in theory of mind, in which you only reason about one specific belief that I know that you know that I know that you know that I know that you know that X, but it's I know that you know that X, but someone else knows that Y, therefore you can infer Z, and I know that you know that Z isn't actually inferred from X. So it's kind of like all of this mix of interactions between beliefs and communication. Right, so what have we actually, well, after modeling it, what can we actually see here? First, deception isn't necessarily caused by lying, right? So there are specific communicative acts that represent lying. So reporting something of the world that isn't true. But if the other agent doesn't trust you or is too skeptical, well, actually, it's not going to work through lying. It might actually be better for you to tell the truth because that agent has a skewed representation of who you are and like the trust in you. And actually, it's better to be truthful in some cases. Importantly, deception happens intentionally and unintentionally. And this is also a function of the BDI model, so of practical reasoning, and of the assumption of intentionality. Sometimes we've explored dynamics in which agents actually did not intend to deceive, so they told the truth, but the context of the situation caused the target to actually be deceived, right? And then, of course, there are all of these factors like the levels of theory of mind, levels of recursivity, cognitive load, skill of deception that actually influenced all the outcomes of multi-agent interactions. And this is kind of like just an extended form representation of the possible deceptions or non-deceptions that can happen in a very simple game. Well, it's simple, like in terms of, there are only two agents that can interact with limited actions, but you can actually see interesting outcomes in terms of whether someone was deceived because of something else. Right. Well, yeah. From this approach, we've learned that, okay, we can represent these mechanics of deceptive communication as inspired by the theories of deception. Because the formalizations were, well, they were rich formalizations, but they can actually be implemented in agent-oriented programming languages. So you can actually engineer these types of interactions and explore multiple scenarios, right? So this is quite interesting. It's in a way, if you use this method, you can easily implement it. And we implemented in the JSON-oriented, agent-oriented programming language. Yeah, of course, theory of mind is crucial. And yeah, we've shown that unintentional deception might happen. I've already talked about that. Okay, good. So we know how deception happens in the minds of the agents. We know how these beliefs can be manipulated based on communication, how different factors influence these interactions. Yeah, but what if we want to simulate lots of interactions? What actually happens at the societal level, and how can we study it? So one interesting concept that we refer to in the work on the social behavioral level is the tragedy of the digital commons. And basically, this is the tragedy of the commons, right, where agents exploit a public resource and, well, they exploit it in such a way as they will lose the resource and then everyone dies. So in the case of the digital commons, knowledge is actually a public good. Think about Wikipedia. Think about all the things you can read on the internet. And you can actually exploit it in different ways, not just in beneficial ways to, improve your knowledge and, help you educate others, or, make progress in science or, whatever. You can actually exploit it maliciously through polluting it or exploiting some bandwidth, so cutting access of other people to relevant information. And it can be caused by humans, right? So think about DDoS attacks, right, and cutting off the resource. But it can also be done by agents. One very good example is a self-replicating malicious, like self-replicating virus on a network. that can delete files, important files, so you cannot access them. Or more recently, you use the GPT-3 bot to generate bullshit and populate the internet with various fake news articles or actually fake science. But that's not necessarily deceptive, but it's one strategy to pollute the infosphere. Right. So in order to kind of like study deception as part of the as causing or affecting the digital commons, we modeled interactions between agents as public goods games. And what we were really interested is not only in modeling deception and seeing if it actually emerges in large systems that manage knowledge, but also we were interested in potential ways in which you can actually reduce deception and reestablish cooperation. And this was kind of interesting in the way that, well, first, when we modeled deception, it was straightforward because we had all of that cognitive aspects of how deception happens. So that was straightforward. But then the problem was, okay, how do we design an interrogation mechanism or something that can actually reduce deception? And yeah, again, the success of reestablishing cooperation or of interrogation mechanisms actually depends on the type of game you're playing. Well, all of the types were public goods games, right? You have a knowledge that is managed publicly. Well, between publicly means 3 agents, 5 agents, N agents, it doesn't matter, but it happens in populations of agents. Right. So these previous works showed that cooperation can be reestablished through social learning. So social learning actually means imitating the behavior of another agent that you interact with. So for instance, if, well, it can mean anything. For instance, if I need to, I don't know, drive from point A to point B and I'm using car type X, and Carlo is using Y, and then I interact with Carlo. It's like, Carlo, how long did it actually take you? Well, only like 10 minutes. Oh, it took me 20 minutes. What are you doing? Oh, I'm actually using this type of car. And then like, okay, I'm going to buy that type of car. So this is one type of like social learning. So it's learning the behaviors of others that generate a higher payoff. But it also implies some sort of mutation, right? It's an evolutionary algorithm through which at random agents of the population actually explore new strategies. Are like, okay, what if I did this? Does this work? And they get a higher payoff. And once they've discovered it and then interacted with another agent, the other agent that used the previous strategy sees the new strategy. It's like, oh, this is so much better. I'm just going to copy it. And this is how the strategies replicate throughout the system. And basically, strategies here in this previous work were represented by cooperation. So cooperation means agents contribute to the public good, so to knowledge, but they can also use that knowledge, right? But everyone needs to maintain it and update it. Think about updating Wikipedia with genuine knowledge from time to time. Defectors that would use Wikipedia but never contribute to it. So for them, there's no cost of contribution. There's just exploitation of the system. But of course, if no one contributes to Wikipedia, in a few years, it just becomes obsolete. So you can't use new knowledge as you've done beforehand when people actually contributed to it. There's the pool punishing mechanism, which is a centralized mechanism for punishing defection, right? So you're punishing, think of like a centralized government that, is investigating and punishing whoever is not contributing. Peer punishment, where the punishment of defectors isn't done in a centralized manner, but it's peer-to-peer. It's kind of like, hey, you didn't really contribute to Wikipedia. I'm gonna call you out, and then you get punished. So yeah, these studies have actually shown that peer punishment, which represents decentralized kind of like in those games we're representing, or in the interpretation of those games we're representing Western democratic forms of government, we're actually very good at governing the commons, better than centralized systems, of course, depending on some assumptions, but also they've shown that if we introduce the corruption strategy in the game, after some time, corruption actually causes the emergence of Western democratic governments, which is like an interesting thing. And then what we basically did was, okay, what actually happens if we introduce deceivers in the system? Right, and we published this in the Royal Society Open Science journal. And yeah, basically we had lots of trials, mainly not because we wanted to see what happens when we introduce deceivers. We've seen what happens, but then the problem was, okay, well, I'll tell you what happens, and then we discuss why we've had six types of games, right? Public goods games. Yeah, mainly if we just have deceivers, this happens. So free riding dominates the system. Free riding means, well, defection and deceptions are free riding strategies. What deceivers do is they exploit the public good, do not contribute to it, but pretend they actually contribute to it. Think about, generating fake news and then trying to hide it for various reasons. So that's what the deceivers do. And if we have peer punishers and pool punishers, well, they can deal with defectors quite efficiently. But when it comes to deceivers, they're like, I have no clue what happened. Like, this person contributed, but they don't actually have the capability of actually checking what the deceivers actually contributed with in the public sphere. They cannot interrogate, hey, where did you get this information? They cannot test whether the information is genuine. And then they cannot simply catch deceivers and punish them. Because to them, cooperators and deceivers, they're all the same. Oh, everyone's contributing, it's fine. But then, free riding emerges. Yeah, the setup was, well, we had different setups, but we mainly presented the results from a setup that was consistent in terms of parameters with the previous studies that I talked about before on like corruption and social learning. So we assume that we have a population of 100 agents. The public goods game is played with 5 agents at the same time. So basically, out of those 100 agents, you sample 5 of them, you take them out of the system, and it's like, play, use your strategies. And then after playing, they get the payoffs. We used 100,000 iterations for each individual run. We had 1,000 independent runs, and every run started with a distribution of all defectors. Sorry, not every run. The initial run started with defectors. The second run would start with the previous state at which the initial run ended. So it was kind of like a loop. Well, you might ask, well, the previous papers that you mentioned didn't actually run 1,000 samples of the independent runs. Why did you run so many samples, like independent runs? And the answer for you is because by introducing and modeling deception, we didn't use a standard way of modeling strategies. We had lots of cognitive functions in there that would actually influence the payoffs at each iteration. Once the state of the world changes, so the distribution of the population, you get a completely different payoff. We model trust, deceptive skill, and all of these are influenced by the prevalence of the other strategies in the system. And what happened then, as it usually happens with these types of approaches when you actually model cognitive processes in evolutionary games, is that you have lots of like cycles and you see strategies fighting each other off. So you run one independent run, you see a certain type of dynamic, and it's like, yeah, it's fine, let's run another one. It completely changes. So then we actually couldn't really see what was happening overall, and we wanted like an overall, like to report an overall result. We want to say, okay, but actually, who dominates? Like in overall, who like what's the what's the actual frequency of the agent? So we had lots of like it was stochastic, and there was like no run, like every run was like completely different from the other one. So then we ran 1,000 independent runs, and then we did the averages of the long run frequencies after each run. So that's how we came up with these sorts of results. Yeah, so we can't, like, you could see what happens in an individual run, but we wanted like an overall picture. Okay, so you've seen what happens if we introduce deceivers. Freewriting flourishes. Cooperators, well, they won't have any information that they can use on Wikipedia. And the punishers actually can't distinguish between cooperators and deceivers. But then we start interrogating them. And based on the previous ones, we're like, okay, let's actually model different types of strategies that can interrogate. So first we had centralized types of government. That this means punishing both deceivers and defectors that would work separately from the people that were actually doing investigating who is deceiving or not, right? So you'd had government that was like, yeah, government that was punishing, and that then you had investigative journalists, for instance, that would investigate, would find out who, why, what, but no one was acting on it because they weren't actually synchronized with the government. Then we had, so first it was a centralized government, that's very important. Then we had a decentralized government that works separately from investigators. So in a centralized government, all the information was like, they weren't punishing deceivers. Like it wasn't a peer-to-peer punishment. Like they were just, if deception was happening, they were punishing everyone they were thinking that they might have deceived in a group. Whereas decentralized ones are kind of like, okay, we are the government, we have the investigators. I'm going to assign investigator and a certain punisher to work, to investigate each individual separately and actually find out what's happening. But the problem was they still work separately from the investigators, even though they were punished. So they were working separately from the investigators, but they were punishing people separately based on what they were perceiving. Then we had centralized governments with investigators working together. So that means the centralized government was having its own, well, was acting on what the investigators were saying. And something like this happens with these setups. Like, it doesn't work. None of them works. If they were catching deceivers, defectors were like running loose, sorry, and the other way around. But what if we had decentralized governments working with interrogators? So mainly here, everyone's cooperating, but everyone has their independence, right? They're acting independently. They can actually test sources of information independently, and they would be able to deliberate about incoming information separately from what's the information declared to be genuine by the centralized institution. And this happens. It's like magic. it works. You have independent investigators with independent punishers that actually work together. And there's no centralized way of actually managing either of these. So there's no like politburo that dictates, oh, you should only investigate this or you should only punish that because this is the policy of the government. It's actually the agents can do their work independently and, you know, act on their best informed knowledge in a way. The only trick here in our previous model from the Royal Society is these are two setups, and this represents social learning. When social learning is weak, well, yes, we managed to, like, cooperation is higher than in the previous setups, but free riding still dominates all of the cycles. Whereas here it does not. What this means is according to our assumptions and the type of game that we modeled, it means, well, good news, you can actually reestablish cooperation in the face of deception. The problem is you shouldn't really make mistakes. So social learning is, needs to be infinite. It's like there's no room for mistake. Everyone needs to act and investigate in a correct manner. If you fail to do that, if there's a corrupter on the line or someone messing about, you can't really do it successfully. Right. So those were the work that I've done in my thesis. And at the end of my thesis, I actually proposed, well, we can understand what happens at an interaction layer, so in the minds of the agents, and then assuming that we can actually explore the dynamics of what happens in societies, what if we actually, you know, connected the two? And then I started proposing this multi-agent systems framework for building multi-agent systems tools for intelligence analysis, such that they can identify deception causation and deception causation prevention. And I listed I listed some desirable properties of this framework. It needs to have first representational power. And that's important because you want to see exactly what type of belief is being updated, changed, manipulated, or acted on. You need to represent various things that go on when agents communicate. You need to represent various cognitive and social cognitive factors. It needs to have some sort of automated counterfactual reasoning. So the idea is that, you know, having a multi-agent system tool, you should be able to say, oh, this is the case, but what if the state of the world was different? What kind of dynamics would you have then? Then it needs to be, well, social interactivity. Yes, well, mainly this is at two different layers of abstraction. First, there's the internal social interactivity between agents that you're actually modeling, and then social interactivity of the tools with the user. So, for instance, the user can just tell the tool, oh, try this setup instead of that. So it's able to socially interact with the tools. One idea is self-explainable AI agents. So you're interrogating kind of like each agent in the system, what it knows or how it reached its knowledge and or how it wants to act. And then there is scalability. Scalability doesn't just only mean scalability in terms of of a model, right? Like we had before 100 agents, we could easily have reported the results of 1,000 agents in the population. What I mean in terms of scalability, I mean scalability in terms of the framework. So this framework ideally should include multiple ways of agents, multiple types of agents, multiple types of agent architectures, various ways of representing communication, and various ways in which agents can learn. And scalability means that you can build upon that. So you can introduce new functions to learn and new architectures. So it should be able to help people modularize all of these models to explore the dynamics. And I just want to mention the people I've worked with that have helped me during my PhD. Peter McBurney and Simon Parsons were my supervisors at King's. Iyad Rahwan and Alex Rutherford were my advisors at MIT, and Raphael Bordini and Alison Pannison were my collaborators for implementing my models in agent-oriented programming languages. So the ones that had to do at the cognitive, like interactional level, because the other large-scale societies, we've done a totally different implementation that was in Python. And yeah, just to advertise that I've also organized a few workshops on deceptive AI. Carlos is familiar with that. He actually gave a keynote talk at one of them. And yeah, if you're interested on the kind of like state of the art or new ways in which new types of research that cover the idea of deceptive AI, please have a look at the workshop proceedings. Some of them are like, actually, most work is quite interesting. And it covers like logical methods, machine learning approaches, conceptual approaches, and implementational approaches. Right, these are the main references. Yeah, so the first paper in AI communications that represents the interaction layer. So what happens inside the minds of the agents when they communicate and how they decide to communicate what they communicate. The second paper is the evolutionary dynamics. So the tragedy of the commons, public goods games. Then there's other papers I referenced, like Greco Floridi's tragedy of the digital commons. This is for you to get familiar with how the tragedy of the commons applies to the digital sphere. Ferris's paper on the intelligence deception complex. This is a very nice paper explaining how intelligence analysts actually understand deception. It's where I got the idea of deception causation and deception causation prevention. This is how people analyze cases of deception, but also in terms of overarching narratives. And the final reference is my PhD thesis, where you can actually find all of that stuff. Right. Thank you for the chance to present this.
Anyone has any questions?
I'll go last because otherwise
I just need to have some water.
We are a bit tight on time, I think.
Oh, hi.
Hello.
Very good talk. Interesting. There's a lot of interesting ideas in there, which I'd like to talk to you about sometime. A lot of the research here, we've looked at influence and spread of ideas and consensus and so on in social networks, usually with a lot simpler agents. But one of the things we found is that you touched on architecture, but we found that in a lot of cases, that's all important, makes a difference, the combination of the way the communication happens and the architecture. And in some cases, the architecture actually changes according to the dynamics.
Yeah.
Have you looked much into that? Because certain sorts of structures that do emerge. And these days, of course, you've heard this idea of the filter bubble sort of idea that cohorts are forming based around consensus bias and so on.
Absolutely, I love that question. Yeah, so all of that, all of which you have seen here, these are foundational steps. And what I want to look into now is network dynamics, how these apply to structures on the web, but also structures in society, because those can have an effect, right? With the networks, you can actually model what's the actual relations between agents, rather than just having an, heterogeneous or homogeneous agent population. Yeah, that's future work that I'm actually starting to model. I've just finished like a network-based, graph-based implementation of it, actually to study these sorts of interactions. Thank you.
Yeah, I think for the sake of time, we may conclude the session here. I think you can have a chat offline with Carlo again. We are 10 minutes past the hour already. Yeah, thank you everyone for tuning in. And thank you very much, Stefan, for your very interesting talk. And hope to see everyone in the next talk. Thanks.
Thank you.